Okay, let's do a problem of finding eigenvalues and eigenvectors for a 3x3 matrix. Okay, so now this is going to get a bit more challenging, at least more involved, but the steps are the same. So first we calculate the eigenvalues. And to do this, the determinant of A minus lambda I must be 0. Now, there is a very common mistake that I see often done by students in exams, and also by me when I'm doing when I'm writing the exam and writing the solutions. It's very easy to make. So normally there is no prefactor in a matrix, and then it's very easy to do A minus lambda I, because you just have to subtract lambda in the elements of the main diagonal, and that's very easy. But when there is a prefactor, you have to be careful. Why? Because it is very tempting to do this. Just write the matrix and subtract lambda to every element in the main diagonal. But unfortunately, this is wrong. And this is a very common mistake. Okay? Why is it wrong? Well, let's walk through it. Let's actually do A minus lambda I. So this is equal to 1/3 of 2, 2 minus 1, 2 minus 1, 2, minus 1, 2, 2, minus lambda times I, which is the identity matrix that has ones in the main diagonal. Okay? So if you explicitly expand this, this is 2/3, 2/3 minus 1/3, 2/3 minus 1/3, 2/3 minus 1/3, 2/3, 2/3, minus lambda 0, 0, 0, lambda 0, 0, 0, lambda. So we subtract these two matrices and we find 2/3 minus lambda, 2/3 minus 1/3, 2/3 minus 1/3 minus lambda, 2/3 minus 1/3, 2/3, and 2/3 minus lambda. Okay, and now we might as well take a prefactor outside, so we can take 1/3 outside, and then we find that this is 2 minus 3 lambda, 2 minus 1, 2 minus 1 minus 3 lambda, 2 minus 1, 2, and 2 minus 3 lambda. And this is the correct answer. Okay, so notice that it is not correct to subtract lambda in the main diagonal if there is a prefactor. Instead, the trick, if you manage to remember, is that you have to subtract minus 3 lambda, because you are accounting for the existence of the prefactor here. Okay, so just be careful with that. That's what I have here written as a common mistake. So knowing that, we can continue with our procedure. So the determinant of this matrix has to be 0, and the matrix is 1/3 times 2 minus 3 lambda, 2 minus 1, 2 minus 1 minus 3 lambda, 2 minus 1, 2, 2 minus 3 lambda. So the determinant of this must be equal to 0. Okay, now the determinant of a matrix so when there is a prefactor, well, let's write it explicitly. This is equal to 1/3 to the power n, where n is the size of the matrix, so 1/3 cubed times the determinant of the matrix without the prefactor, right? So remember this property of determinants. That when you scale the whole matrix by a number, you scale the determinant by that number to the power n, where n is the size of the matrix. So this means that if we are interested in this being equal to 0, we can just cancel this out. Okay, so in practice, you can just ignore the prefactors when calculating the determinant equal to 0. Okay, so we need to calculate the determinant of this matrix here. I suggest using the rule of Sarus. Okay, so applying the rule of Sarus, we have to do this diagonal plus this diagonal plus this diagonal minus this diagonal minus this diagonal minus this diagonal. Okay, the rule of Sarus. So let me write it quickly. This is the first diagonal, this times this times this, then plus the second diagonal, which is going to be this times this times this, then plus the third diagonal, which is going to be this times this times this, which is minus 4, and then minus this diagonal, minus 1 times this times minus 1, so that's going to be minus 1 minus 3 lambda, minus the second diagonal, which is going to be this times this times this, which is going to be 4 times 2 minus 3 lambda, minus the third diagonal, which is this times this times this, which is going to be 4 times 2 minus 3 lambda. And this must be equal to 0. So now you can see that the left-hand side of this equation will be a polynomial of lambda. In fact, it will be a polynomial of degree 3, because at most we are multiplying 3 lambdas together. Okay? So by expanding this polynomial, I won't go through the steps. You know how to multiply brackets out. Yeah? So you arrive at minus lambda cubed minus lambda squared plus lambda minus 1 equals 0. So indeed you see that we have gotten a cubed polynomial. Now this is a general result. When a matrix is n by n, so a square matrix with n rows and n columns, the characteristic polynomial is always a polynomial of degree n, which means that it always has n roots. Okay? Great. So if you factor out this polynomial, you arrive at 1 minus lambda times 1 minus lambda times minus 1 minus lambda equal to 0. That is the factored out polynomial. So our characteristic polynomial, p of lambda, has roots that are given by the first root is 1, the second root is also 1, okay, so actually, okay, let's keep it like that, and the third root is equal to minus 1. So sometimes it does happen that 2 of the roots are the same, and this is given a special number. These are called degenerate eigenvalues. So these are degenerate eigenvalues. Okay, and later we will learn about what's the significance when this happens. But with this we have finished the first step, which is calculating the eigenvalues. Okay, so these are the 3 eigenvalues. Or we could call them the 2 eigenvalues. One of them is being degenerate. Okay, so next we have to calculate the eigenvectors. For each eigenvalue. So for lambda equals lambda 1, which is equal to lambda 2, which is equal to 1, we can do them together, right? Because they are the same eigenvalue. So now we need to solve the system. A times b equals lambda times b, where we substitute lambda equals 1, so I can just erase lambda. Yeah? So we need to solve this system. Or we can solve the equivalent system that a minus I times v equals 0. Okay, so we can solve, we have a minus lambda I, we have it here. This is a minus lambda I. So we can simply substitute lambda equals 1 and obtain this matrix that will be a minus lambda I. So let's do it. We get that 1/3 times, so that will be 2 minus 3, that will be minus 1. Then we copy the other elements, 2 minus 1, and then in the second row it will be 2 minus 1 minus 3, so it will be minus 4, 2, 2 minus 4, 2. And then the third row will be minus 1, 2, and 2 minus 3, which is minus 1. So minus 1, 2, minus 1. So this multiplied by v, which is vx, vy, vz, equals 0, 0, 0. Now, this is a 3 by 3 matrix, and we have all sorts of coefficients. So rather than doing it the old-fashioned way of writing the three equations and then start to subtract and divide one by another and so on to try to solve the system, I would recommend, being a 3 by 3 system, to solve it using Gaussian elimination. Okay? So let's do it. First of all, we can cancel out the prefactor because we are equaling to 0, and therefore the prefactor can be cancelled out. So let's do it, let's solve it by Gaussian elimination. So we begin by writing the augmented matrix. With a bar, and then the independent coefficients, which are all zeros. Now, as I have repeatedly said, we know that the determinant of this matrix is 0. How do we know it? Because this matrix is A minus 1 times I, and we designed this determinant to be 0. That's how we found lambda equals 1. Okay, so we know that A minus I has a determinant equal to 0, and therefore we know that this system of equations will have at least one of the rows which cancels out, but we don't know which one yet. Okay, so that's why we can do Gaussian elimination to find out. So let's start with Gaussian elimination. Let's start with the pivot of the first row, and we are going to use that pivot to create a 0 here. So therefore we are going to do row 2 plus twice row 1, and the result we place it into row 2. So what we get is, first copy the first equation, and then we get 2 minus 2, 0, minus 4 minus 4, sorry, no, minus 4 plus 4, 0, and 2 minus 2, 0, 0 minus 0, 0. Okay, what about the third equation? We want to have a 0 here, so we can just do row 3 minus row 1. We put the result into row 3. So minus 1 minus minus 1, that is 0. Then 2 minus 2, that is 0. And then minus 1 minus minus 1, also 0. So interestingly, in this case, 2 equations were all zeros. Okay? So this means that we will have 2 degrees of freedom in this solution. Okay? So let's find the general solution in Gaussian elimination. We have this as a pivot, but the second row doesn't have a pivot and the third row doesn't have a pivot, and therefore these 2 columns don't have pivot. And so x2 and x3, we know that they will be free variables, okay? But in general they will be different free variables. So our solution to this system is that x2 equals alpha, sorry, Vy equals alpha, and also Vz equals beta. So in general, it's going to be a different degree of freedom. And now from row 1, we know that minus 1 Vx plus 2 Vy, which is alpha, minus 1 Vz, which is beta, equal to 0. And therefore we know that Vx equals 2 alpha minus beta. And that is our general solution. So V, which is equal to Vx, Vy, Vz, is equal to 2 alpha minus beta, then Vy equals alpha, and Vz equals beta. And this can be written as alpha times 2, 1, 0, plus beta times minus 1, 0, 1. That's how we can write the general solution. It becomes the equation of a plane, okay? So, as promised, the determinant of this matrix was 0, so we know there were infinite solutions. In the previous examples, we just saw that the solutions were a line, an infinite line, but sometimes the solutions are a plane because we have two eigenvectors associated to this eigenvalue. Okay, so we could say that for eigenvalue equals 1, we have two eigenvectors. So we would call them v11 equals 210 and v12 equals -1, 0, 1. And this is the solution for this eigenvalue. Okay. Now, if you want to be more technically correct, you could say that the eigenspace associated with lambda equals 1 is equal to the span of these two vectors, 2, 1, 0 and -1, 0, 1. So any vector inside of this plane will be an eigenvector with an eigenvalue equal to 1. Okay? So this matrix is leaving all of the vectors that are inside this plane, inside this span, they are leaving those vectors unchanged because the eigenvalue is 1. So A times V equals V. Okay? So that was for the first two eigenvalues. Now we need to do it for the second eigenvalue. So for lambda 3 equals -1, we need to solve the system for lambda 3 equals -1. So once again, we need to go back to the matrix A minus lambda I, and we need to substitute lambda equals -1. Okay? So I'm going to do it. I'm going to do it fast rather than keep looking it. You just know that we just put lambda equals to -1 and we find this matrix. So let me do it quickly. A minus -1 times I, V equals 0. So this means that A plus I times V equals 0, and the matrix is this. So this times V is equal to 0, 0, 0. Okay, so now we need to solve this system of equations. And once again, we know that at least one of the equations will be redundant. We will get 0 equals 0, but we don't know which one. So we are going to proceed with Gaussian elimination. So let's first write the augmented matrix, and we can get rid of the prefactor because we are making it equal to 0, 0, 0. So the augmented matrix is this matrix here. So we start with our first pivot in the first row, and we will have to make this 2 equal to 0. So the way to do that is that we get row 2 and we subtract 2/5 of row 1 and we put the result into row 2. So after copying the first row, the second row will have a 0 here, then we will have 2 minus 2/5 times 2, so that will be 2 minus 4/5, which is 6/5. And then we will have 2 minus 2/5 times -1. This is getting a bit complicated. Let me just write it down temporarily. This is 2 minus 2/5 times -1. Yeah, I'm doing this minus 2/5 times R1, which is -1. And the result of this is equal to 12/5. So that's what I write here. And then 0 minus 0 equals 0. Okay, so we have the second row, and now we have to do the third row. So for the third row, we want this to go to 0. So what we are going to do is R3 plus 1/5 of R1, and we substitute it into R3. So we will get, the first one will be a 0, the second one will be 2 plus 1/5 times 2, which equals 12/5, and we will have 5 plus 1/5 times minus 1, which will be equal to 24/5 and 0 here. Okay, so Gaussian elimination, you know the procedure. What we can do now is we can multiply by some factor to simplify these equations. Okay, so we can actually multiply the second row times times 5/6, and what we will get is 0, 1, 2. And then the second row we can multiply it, sorry, the third row we can multiply it by 5/12, and we will get 0, 1, 2. Okay, now we see that the third row is equal to the second row, so we can actually do R2 minus R3, we place it into R3, or the other way around, R3 minus R2, we place it into R3, and the result is that the third row goes to 0. So as promised, always at least one of the rows goes to zeros. Yeah, because we designed the determinant of this matrix, we know that this determinant has to be 0 because that's what we designed in the first part of the problem. Yeah, that's how we found lambda equals -1. So since the determinant of this matrix is equal to 0, we know that the solution to this system must have at least 1 degree of freedom, and that's why one of the equations disappears. Okay, so now the pivots are here and here, so now this has no pivot. So this means that vz is going to be a free variable, so vz equals alpha. But there are no more free variables this time. So now we do inverse substitution to find Vx and Vy. So from the second row, we have that 1 times V1 plus 2 times Vz, sorry, 1 times Vy plus 2 times Vz, which is alpha, equals 0, and therefore Vy equals -2 alpha. And then from the first row, we have that 5Vx plus 2Vy, which is -2 alpha, minus 1 Vz, which is alpha, equals 0, and therefore Vx, or 5Vx, is equal to 5 alpha, and therefore Vx equals alpha. Okay, so our final solution is that V equals Vx, Vy, Vz equals what? Vx equals alpha, Vy equals -2 alpha, and Vz equals alpha. So this is equal to alpha times the vector 1 - 2, 1. And we know that this will be our eigenvector. Therefore, for the eigenvalue lambda 3 equals -1, we know that the corresponding eigenvector is equal to 1 - 2, 1, or any multiple. And this is our final answer. Or if we want to be more technically correct, we can say that the eigenspace is the span of this vector here, which will be the equation of a line, an infinite line in 3 dimensions. Okay, so we solved a long problem of eigenvectors and eigenvalues in a 3 by 3 matrix. Excellent. See you in the next video.